Hi everybody, welcome to our next lecture in magnetism, where today we're going to continue looking at the effects of magnetic fields on moving charges and then also the effects of a magnetic field on a current carrying wire. In this picture we have a positive charge that is moving to the right with a certain velocity, and it is going to enter a very large magnetic field. Now keep in mind, as the charge moves, it has its own magnetic field, okay, because moving charges generate magnetic fields. So right now, though, there is no magnetic force because it's outside that other large field. But the moment it enters the field with that velocity, now it's going to experience a magnetic force. Now, if we do our right-hand rule, we would take our right hand, our thumb would point to the right, our fingers would then point into the page, and that would give us a magnetic force pointing up. Now, if you think about it, as a charge moves to the right but experiences an upward force, that's going to cause a change in direction, so that now it's going to be moving kind of diagonally. But by the right-hand rule, that means we sort of need to tilt our hand so our magnetic force now points this way. Well, that in turn will cause the charge to change directions again. So it's now moving up, making the magnetic force point to the left, which would then cause the charge to move diagonally again, making the magnetic force kind of that way, which would then cause the charge to move again. So if we kind of follow the path of the charge, notice the shape we're getting here, a very curved path. But more importantly, notice what direction that magnetic force is pointing at all times, towards the center of that curved motion. So what does that mean to us? Well, if the magnetic force points towards the center of any circular motion, it can be considered a centripetal force. Yes, good old circular motion is back. So, charges that travel in large magnetic fields travel in circles or along any curved path upon entering that field. So again, that must mean that the magnetic force is a centripetal force. Okay, if there's only a magnetic field acting on the charge, the magnetic force causes it to move in a circle and therefore is a centripetal force. Now we have these two equations for magnetic force, BQV, and if we remember, centripetal force was mv squared over r if we have a linear velocity, and mr omega squared if we have the angular velocity. So let's look at an example problem in this situation. I have a 9 nanocoulomb charge with a mass of 5 times 10 to the minus 22 kilograms, traveling at 6 times 10 to the 7th meter per second in a 0.25 Tesla magnetic field, and I want to determine the radius of its path. Now, keeping in mind that, as we just said, that as it travels through the field, it's going to move in a circle. So just like back in circular motion, our most important thing was to say, okay, what is the centripetal force? What is Fc? And in this case, it's the magnetic force. Now we can do that substitution, because where I have magnetic force, I can put in the equation for magnetic force, BQV. Where I have centripetal force, well, I've got velocity in meters per second, so I want the linear equation, mv squared over r. Quick little algebra trick. I can cancel one of my velocities here. And then I want to solve for the radius. Well, again, a quick little algebra trick is sort of to exchange the positions of these two things. So r comes up, and b and q both go down on the bottom. Now I can plug in my numbers. Mass, 5 times 10 to the minus 22 kilograms. Velocity, 6 times 10 to the 7th meters per second. Magnetic field, 0.25 Tesla. And a charge of 9 nanocoulombs, again, nano 10 to the minus 9. And that gives me a radius of 1.33 times 10 to the minus 5 meters. Okay. And that's really all there is to that. And again, this is an effective way of understanding something about magnetism. It's actually one of the ways that we can, for example, know the mass of something by shooting a particle into a magnetic field at a set velocity. And if we know the radius of its curvature, we could actually solve for the mass in that case, which is sort of another type of problem, but it's one of the ways we can actually determine the mass of these charged particles. So that's the idea of a charge moving through a magnetic field. It moves in a curve and therefore can create a centripetal force. But now what happens when you have not just a charge, but current going through a wire? Okay, now current going through a wire is not one charge, but lots of charge moving all at once. And that means that that wire generates a magnetic field. Now, if we place that wire inside another magnetic field, we'll get a magnetic force. Okay, so it's actually possible to sort of levitate a wire inside a magnetic field if you have a current running through it, because you can create a magnetic force. Now, we can't use BQV here because we're not talking about one charge with a velocity. We're talking about a lot of charge, okay, that generates a current. So there's a different equation here for magnetic force on a current carrying wire, BIL, okay, where B is still field, but I is the current, and L is the length of the wire that's actually inside the field. Okay, pretty easy to remember, right? And then we can still apply the right-hand rule, where now our thumb is the current direction instead of the velocity direction. So let's look at a simple example here. I have a 0.2 amp current running through a wire that is inside a 0.8 Tesla magnetic field, and 40 centimeters of the wire is in the field. And I want to know the magnitude and direction of the force. Now again, keep in mind, if the current is running to the right, it has its own magnetic field traveling in circles around it. Okay, it has its own magnetic field. Now we don't care what that is because we're putting it inside another field. So to calculate the magnitude of the force, just the amount, oh, that's BIL. Okay, so here I have a magnetic field of 0.8, a current of 0.2, a length of 0.4 meters, 40 centimeters, which gives you a magnetic force of 0.064 newtons. That is for the magnitude. Now the direction. Well, now my thumb points to the right because that's the direction of the current. My fingers point into the field, and that creates a magnetic force going up. So the direction of the magnetic force is up the page. Okay. Now again, that's interesting because, like I said, you could actually float a wire inside a magnetic field if you have a current and a field that's strong enough. Okay. But if you float a wire inside a magnetic field like this, well, that requires that the magnetic force is up, but what force would be down? Well, if it's floating, it's got to be gravity, right? And if it's floating, that means it's in equilibrium. Some of the forces on it are zero. So we should know now that whatever magnetic force you would have would need to support the weight of the wire for it to float. And that's basically it. That's the idea of a charge moving through a field. It can travel in a curved path. And then the current on a wire generates a magnetic field. If we place that in a second magnetic field, we get a magnetic force. That's it for the magnetism. See you next time.